This last century has seen incredible strides being made in how we treat disease, all the way from cancer and infectious diseases to non-communicable diseases like diabetes. But we've still got a long way to go in terms of improving our health and our well-being. Nanotechnology can help here by enabling diseases to be diagnosed earlier or delivering drugs to where they're most needed in the body. It can even help by replacing worn-out tissues like cartilage, for instance.
Cartilage is a soft, tough tissue that is everywhere in our body. It keeps our nose and our ears in shape, but for this project, more importantly, it's used as a cushion in joints where it prevents friction between the bones.
And what is it that makes cartilage hard to replace?
Cartilage is one of the few tissues that doesn't heal. It doesn't regenerate itself. So when it's damaged, surgery is often the only option. The basis of this project was the idea to create a scaffold, effectively a mold, that mirrors the complex structure of cartilage in the body. To do this, we use nanofibers in the polymer. We process these materials into a porous structure. And we use that porous structures to grow cartilage cells. The scaffolds really tells the cells how to grow and directs them to adopt the structure that we find in the natural material.
So in your laboratory, you've been developing artificial cartilage using engineered nanomaterials. How successful has that artificial cartilage been?
So all the tests that we've done in the lab so far are really exciting, but so far we haven't tested this material in humans, and this really would be the next step to validate the viability of this approach.
Artificial cartilage needs to be durable, but sometimes we need implants that do what they need to do and then disperse when their work is done. One exciting area of research here is the use of intentionally designed nanometer-sized particles or nanoparticles in materials that are designed to help reconnect blood vessels in the brain.
So in this case, nanoparticles are used, they are put in a patch around the vessel. Then we insert a laser in the blood vessel, and the laser light then solders the blood vessel by heating up the nanoparticles.
So your research involves trying to understand the possible impacts of these nanoparticles on our bodies when they're released, but you've been doing this outside the body at the moment.
We started with a very basic model looking at monolayers of different cells that occur in the brain to see if nanoparticles were taken up, what happens to them, all kinds of toxicity tests. In the next level, we used a more complicated model where you have a mixture of cells. And then in the third part, we used brain slices which come very close to reality.
So how significant do you think the possible risks are compared to the benefits of this technology?
When you look at what we did, we used a large amount of nanoparticles, put them into the cells. So we investigated the worst case scenario, and overall the tests, I can say, there is not much indication, or basically no indication for adverse effects.
Nanomaterial-based implants are all about putting beneficial nanomaterials into our bodies. But we can also use nanotechnology to create materials that can take harmful stuff out of our bodies. One way we can do this is to make nanoscopically small particles that can mop up and remove toxic substances in our blood.
We have quite often clinical scenarios where we have toxic substances in the blood which are harmful and detrimental for the patient.
So how are you trying to solve this problem?
We have the blood outside of the body, and then we inject nanoparticles into the bloodstream, and these nanoparticles are covered with catching agents to catch proteins, to catch metals, and then we add a magnet to eliminate these harmful substances together with the nanoparticles. This has been very successful with regard to proteins, to metals, and now we try to figure out if we can apply this approach also for cells.